Well, thanks so much. I'm Sam, Sam NM5N. I know we corresponded back in this, I think, December, January timeframe. I found your YouTube video on dealing with RFI noise and more specifically about dealing with power line noise. And I just thought it was a really great presentation. And I thought it'd be a great idea for, if you could, share some of your wisdom with the Cowtown Amateur Radio Club. And without further ado, I think I'll just go ahead and turn it over to you.
Okay, sounds good. Well, I appreciate the opportunity to talk to the group, and hopefully we'll all learn something tonight. I'm always in the in the learning mode when you work on RFI. As Sam mentioned, my name is Jeff W4DD. I live in North Georgia, north of Atlanta. I'm going to talk about RFI tonight, receive RFI for the most part. And I'll talk about some of the things I've learned over the last 20 years and some of the bunny trails I've traveled down trying to solve problems. And there's plenty of those when you work on RFI. So I'll talk about 6 topics tonight. What is RFI? Do you have it? Some tools, first some simple tools, and then some better tools to use. And then examples. Some clearing distance guidelines, how far out you need to look for noise problems, and then some results I've achieved here at my station. So what is RFI? It's an acronym, radio frequency interference. Very broad term used to describe an undesirable signal that interferes with the reception of a desired signal. Why do we dislike it? Well, the receive RFI raises the base noise floor, and the higher the noise floor, the fewer signals you're going to hear. So it's in our best interest to increase the signal and decrease the noise to produce a better signal to noise ratio. So even when the noise floor is low, or when the noise floor is low, even weak signals are very readable. There's no problem reading S1 signals as long as the noise is low. Many kinds of devices today generate noise. Power lines and switching mode power supplies are the 2 most common. Not unusual to have multiple devices inside of a home causing problems. So power line noise, first category, it's energy generated by high voltage arcing, usually caused by unintended arcing between 2 metal conductors in a power pole. It is, in simple terms, a spark gap transmitter from 100 years ago. And the effectiveness of that transmitter is the intensity of the arc, in other words, the power, and the antenna, or the power lines that are connected to it. And it can go from basically S0 to S9 plus, I think the highest I've seen is 50 dB. And that's a pretty big signal. And by the way, if anybody has any questions during the presentation, you're more than welcome to ask them. If they're short questions, I'll try and answer them right then. If they're a longer question, I'll delay it till the end of the presentation. Many kinds of causes for power line noise. Defective insulators, pretty common. Lightning arresters, and also metal-to-metal arcings on some of the brackets and the pole supports. One characteristic of PLN, usually a wideband noise, so it ranges all the way from 160 meters through VHF and even UHF. Switching mode power supply, different animal. SMPSs are very common for powering electronic equipment nowadays. You see very few linear power supplies, or almost all SMPSs. And one of the ones I see very frequently is the battery chargers, usually used on lawn tools, sometimes on dust busters. If it charges a battery and it's a high current SMPS, they generally make noise. And I find them almost anytime I go out and do an RFI assist. As I'm looking around, I'll ask, what's in the garage or what's in the basement? And they say nothing's plugged in, and we'll go in, and sure enough, there's a battery charger there charging a lawn tool battery. The reason they're used, they're more efficient, less expensive to produce than the normal power supplies we saw, say, back 10, 15 years ago. They generally use a small transformer that operates at frequencies much higher than 60 hertz, usually 15 to 50 kilohertz. And if they're not well designed, they can generate a lot of noise, and it usually affects the low bands more than the high bands. So it's another characteristic that may help you determine what's causing the problem. So why do we need to understand this? Well, a lot more digital devices in our homes. Digital devices have lots of square waves. Square waves have lots of high frequency components that range into the RF spectrum. Poorly designed SMPSs generate lots of HF noise, and they try and push that cost lower and lower, and sometimes the parts that should be on the board are not on the board. So if you get a good one, that's great, but maybe 10%, certainly 5% of the SMPSs I see are problems. And the third thing, many power companies are moving from the 7 kV distribution lines to the 14 kV. That happened to me about 10 years ago. Twice the voltage, I find, is about 4 times the problems. So you see a lot more PLN problems when they move over to the 14 kV lines. So why do we care about the noise floor? Well, I took 2 snapshots here with and without noise. The first one was in 40 meters, had an S7 noise floor, which is kind of high. I counted 11 workable stations. And a few minutes later, the noise went away. Same snapshot, the noise floor was now S5, and I counted 17 workable stations. So 2 S unit decrease in the noise floor, 50% more stations could be seen on the pan adapter. So that's the reason we want to push that noise floor as low as we can. It's not always possible to get it to 0, but we want to push it low. So do you have RFI? Well, you power up your HF radio. You pick the band and antenna of choice, find unused frequency. You set the mode to AM, much easier to diagnose problems in AM mode. You should hear a nice gentle hiss. And if you hear a raw buzzing noise or see a strange signal on your pan adapter that's not ham generated, that's another sign you may have RFI. So if you do see those characteristics, you need to investigate further. So I have an example of PLN here, and let me turn on the sound share so you can hear it. So I think you can hear that buzz. It wasn't real loud, but could you hear it okay?
Yeah, yes, sir. We did.
Okay. So you listen to it, and it's very even. There's no variation. We hear some sputtering, but there's no, and I call it intelligence in there. Many times in digital transmission, and you have RFI from digital devices, you can kind of say there's some kind of intelligence back there. With PLN, it's very random pulsing. And you'll see it typically in the pan adapter as snow across the entire screen. Just white dots is what I see on my Flex radio. And it's usually pretty easy to diagnose from that. And also it ranges well up into 10 meters and beyond that. And you can see in this case, it was about 15 dB over S9. So it was pretty strong. It's going to mask a lot of signals. So what do you do if you have that? Well, the first thing, or the first question I ask is, what does it look like as far as a by band comparison? You know, look at the 5 major bands. What's the S meter reading? What antenna are you using? And I like to get a feel for, is this thing tapering off at higher frequencies, or is it just as strong at 10 meters as 80 meters? That usually tells us something about the potential source. And then the second thing, if you have a directional antenna, fantastic. I frequently take readings every 30 degrees from my Yagi. So 12 total readings, and that will give me a pretty good idea of the quadrant I need to look. So I know, hey, this is a northeast problem. If you really want to zero it down, if you have, you know, like a 4, 5, 6 element Yagi, you can get it down to plus or minus 5 degrees typically. So it's a very valuable indicator of at least the quadrant you should look in, and potentially even the actual direction that you can plot on Google Earth. Those are the first 2 questions I usually ask. So some simple tools, very simple tools. First is circuit breaker test. The scale is your house or your neighbor's house. Start by turning off all the breakers and see if there's any impact. And if there is an impact, and you start turning them on one by one and see which one of the breakers is causing the problem. And when you find one that's causing a problem, make a note of what it serves. You turn it off, and then continue down the list until you've done all of your circuit breakers, because you could very easily have more than one source of RFI. It works really well if the noise is inside your house and you control that noise, or your neighbor's house if they're cooperative. The second very useful tool, a portable AM radio. You can walk around within a few hundred feet of your house, kind of get an idea of, hey, is this thing close or not close? The negative is it doesn't provide the magnitude. You get a kind of general indication of the strength, but not a very good one. And you don't get a real good indication of the location either. That's the two characteristics I look for, location and magnitude. And then the third tool, very simple tool, AM car radio. You can drive miles, so you can cover a lot of territory. You drive around listening for the same noise as the noise you hear at your home station. Again, it doesn't provide magnitude, but it does provide a reasonable look at location. And one of the things I always emphasize, noise could be a small source inside your QTH or a big source farther away. And when you first start out, you don't know which one of those two it is. Could be, small and close or big and far away. So keep that in mind. And you always want to clear the small or the close stuff first. So much better tools, the tools I like to use most often. First is 137 megahertz Yagi with an HT and an attenuator. The scale is, you can cover blocks pretty easily. Very useful for anybody. It's a very simple tool to build. If you only build one tool, this is the one because it's so versatile. It works at VHF, and it provides both magnitude and direction. You can point it, you can narrow things down, and then the magnitude can be measured with the attenuator. I find the S meters on HTs and radios are not very useful for RFI hunting. I use the attenuator all the time, and you need something around 45, 50 dB. Second, very commonly used tool, ultrasonic dish. So once you find the pole, if it's a power line problem, you want to ID the part. And it provides both a magnitude and hardware ID, so location. It's an audio device, not an RF device, but that's okay. That's still very useful confirmation of the part that could be causing the problem. And the third tool I use very frequently is something called RFI Mapper. Very useful for hams where you have towers and you have to look out farther, like more than a quarter mile, half mile. And it provides both location and magnitude in a very visual form. We'll talk about that a little more. But I use these tools all the time. Every time I get an RFI cyst, I usually work down these until proven otherwise. So for the Yagi antenna, it's a really fantastic tool. For the cost, you can't beat it. It's basically a very, very low cost tool. I'd say it's essential for finding local noise, and I call that LAN, L-A-N, rather than local area network, local area noise. And it's also very useful for field assistance. If you're working with a power company, you want to be out there with some kind of tool where you can hear it and they can hear it too. That always makes an impression when they hear what you're hearing. They go, yeah, there's something going on here. And when he points at that pole, that's the problem pole. The one shown in the picture is one I built maybe 15 or 20 years ago. And it was intended as a prototype just to see if this thing was going to work. But it's worked so well, I've never rebuilt it. And I've used it. I'm not sure if I'm up to 1,000 times yet, but it's well worn to say the least. The attenuator is a rebuilt one. You can buy attenuators on Amazon actually for about 25 bucks, but this is one I had a case and the slide switches were defective. I had to replace those, replace some resistors inside of it, but the case was a convenient place to start. I frequently get asked why 137 megahertz, and there's some good reasons for that. AM works best for finding noise, and some of the HTs only do AM in the aircraft band. Not all, but many HTs. The second thing is, excuse me, ham radio HTs will not transmit in the aircraft band. So if you hit the PTT button, you're not going to smoke the attenuator. The attenuator has little 1/8 watt or 1/4 watt resistors that will not stand up to PTT. So if you're outside the ham band, you can't smoke it. And that's a good thing, because if you're working with a power company, you don't want to, be helping them and all of a sudden you mess up, or maybe the HT gets wedged between your belt and something else. PTT goes on and it smokes and you're out of business. You can't help them. So I like to stay away from those kind of scenarios. I find that the VHF band provides good range and good pull resolution, both those things. Some people like to use UHF. I find VHF better. I can get range up to 1/8 of a mile, no problem, maybe even 1/4 mile if it's a big problem. So I like that provision. And there's a nice quiet frequency at the top of the aircraft band. 136,950 is where I normally sit. Any questions so far?
I have a question for you. Are these slides going to be made available after the presentation?
If you'd like. The only thing I ask is you not post them on the internet, but for your own use, yeah, I can provide them to Sam or someone else, and he can, or you can just drop me a note, but I can send them over to Sam if you'd like.
Oh, that'd be great. Nice.
And I will say too that we are recording this, so if we will have that as well. And,
okay.
If you're taking photos, we will have this recorded. So.
Okay.
I have another question.
Sure.
You're using an HT as a receiver on this. Is there any reason why you're not using some of these very small spectrum analyzers?
No, you could. I've played with some of the spectrum analyzers, and I come from an era where spectrum analyzers were $40,000 or $50,000, and the sweep rates were very fast. Some of the newer ones have slow sweep rates, and I find that annoying. I don't like to work with it that way. And the other thing is, I can move a lot faster if I can just do it at the audio level. In other words, I can sweep left to right across to azimuth over and over again, and I can hear the results instantly. You can do the same thing with a little spectrum analyzer, but it's going to be a little slower because you kind of have to watch it. And the other thing is that attenuator is going to be a great asset. What I do is I flip in enough attenuation where I only hear the noise in one direction. So it's a very binary thing when I'm hunting power line noise. I put in 30, 40 dB of attenuation, and all of a sudden I don't hear anything except when I'm pointing at the exact direction the noise is coming from. With a spectrum analyzer, you may have a little more problem doing that. Now, for switching mode power supplies, a spectrum analyzer could be a very useful thing because you're looking for a signature there. And sometimes, you want to see, am I chasing the right thing? So there are cases where it comes in really handy. So some hints that I've learned over the years, and basically it's, I call them bunny trails I've traveled down and been trapped on and made a mistake and had to go back and redo some measurements or something. I find that the HT system with the Yagi attenuator, it's really a must-have if you're going to work with a power company. You want something where they hear the noise too, because that's going to motivate them like, hey, yeah, this is a problem. And as soon as they touch something, they'll hear that change. I usually turn the speaker up so they can hear it too. And they go, oh, I just touched something and the noise went away. So it can be a very useful tool. Second thing is the loudness is not always indicative of the RF level. So power line noise and other noises can sound very bad. When I go to measure the actual strength, it's only a 3 dB or a 6 dB noise. And I'm going, gee, that's not very strong, and I'm a long way away from the QTH. That can't be it. So I always go by RF level, and I measure that RF level with the attenuator. My little attenuator is a 0 to 45 dB attenuator, and I've kind of come up with a system I use to classify the strength of the noise. So I flip in enough attenuation where the noise goes away, and if it took 0 to 12 dB for the noise to go away, that's kind of a small source. It's going to have to be pretty close to the ham's QTH to affect them. If it's in the 13 to 24 range, it's medium. It can be a block or two away, and it's going to bother them. If it's 25 to 40, that's getting big. Now you're thinking, hey, this noise source, if it's within maybe a half mile, you need to really consider it as a possible problem. And if it's more than 40 dB, it's really a big noise source. Those are usually lightning arresters, not always, but that's a kind of a direct arc kind of a problem. And if you get above 50 dB, I'm thinking lightning arresters in most cases, or a direct arc between a high voltage point and ground. One of the things I've learned is poles with lots of high voltage lines in them, they may seem to be the cause of the problem, but it may be an adjacent pole with just one high voltage line on it. So the high voltage wires are antennas. If there's a lot of wire on a pole, it's going to be a better antenna typically. So you have to kind of consider that. And the way I compensate for that, when I'm measuring strength of poles and deciding whether it's on my left-hand side or my right-hand side, I stand midway between the two poles. So you equalize the distance, and distance is really an important factor. And I do an A-B comparison when I'm flipping in the attenuation, and sooner or later, when you flip in enough attenuation, you go, hey, I don't hear it to the left, but I do hear it to the right. I need to go to the right, walk down that way, and do the same thing with the next pole. Second tool I'll use frequently is an ultrasonic dish. Really nice to have. The commercial ones are fantastic. There's one made by Radar Engineers, which is a great piece of equipment, but they're really expensive. They're like $4,000 now. So I ended up cobbling together a bunch of different pieces to make what I wanted to use on these problems. Usually you're going to be the RF expert. The power company folks really don't deal with RF enough to be really knowledgeable about it, but they know the power system really well. They know power hardware. So what typically happens is, you're responsible for finding the pole, getting them to the pole, and then they're responsible for the pole itself. I'd say about half of the power companies have an ultrasonic dish themselves. They can bring it along, they can scan the pole and go, it looks like it's a pole top insulator or a lightning arrestor, and that'll get them to the problem much quicker. I added a scope to mine after using it for a while. I wanted a more precise way to find the part on the pole, and that has really helped me a lot. I can usually resolve it within a few inches of the issue on the pole with the scope.
Schematic question.
Sure.
So how do you, using an ultrasonic dish, how do you see the noise in an ultrasonic dish? Now, ultrasonic waves.
I missed the question. How do I what?
It's not in the RF spectrum, all right?
That's correct. That's correct. So you're switching from an RF device that says this pole is a problem to an audio device. But if you think about like an arc, if you walk up to a electrical plate after you've rubbed your feet on the floor, when you get near that ground screw on the plate, you hear a snap.
That's so what you're just listening to the audio portion.
That's correct. The dish is an audio device. It hears that snap, even though you don't. And those dishes have audio gain on the order of 40 dB. They're pretty significant things. And the electronics has a high gain amplifier, 40, 50 dB worth of amplification. So it hears that snap, and it appears as a 60 hertz growl in the dish.
Okay, thank you.
Yep. Good question, though. Very good question. So power pole hardware. What is the stuff on a power pole? Well, here is a simple pole. It's a single phase pole. There's just one high voltage line on this. And this is a 14 kV. You'll see the pole top insulator. You'll see the lightning arrestor, which is this little vertical thing with fins on it. And we'll talk about that more in a second. You'll see an insulator, which is a big white thing, and then it supports another thing that's actually a fuse that they can pull that fuse, and there's a little hook on the fuse. They can pull that hook down, and it pulls the fuse out of the fuse holder. They call this a cutout, is the typical term that the power crews use. You'll see usually a bell insulator or some form of a bell insulator, and it actually kind of looks like a bell, usually a 2 or 3 section bell. There'll be a neutral wire at the bottom of the pole. And the most common things I see, pole top insulators, lightning arresters, and the bell insulators. these bell insulators have metal joints between the different sections of the bell, and when they get really old, they corrode and they don't make good contact, and they start arcing between the metal joints. Those metal joints are held together with a bolt with a pin on it. One word of warning: never touch power pole hardware. There's a fault condition going on here. You don't know what the fault condition is, and you don't want to touch something that happens to be energized, even though it shouldn't be energized, and get electrocuted. And you don't last long at 14 kV. That's enough to stop you in your tracks. So you can look, but never touch.
I've got a question also before you move on.
Sure.
How do you motivate the power company to fix anything?
Well, that's a good question also. I don't have it in this presentation, but I have a little summary. And usually the person I'm talking to will know who his power company is. He'll turn in a trouble ticket, and I send him a report when I do an RFI assist. And that report has basically all the things we're talking about tonight. I'm going to send him a map showing where the noise is. I'm going to send him a drill down map showing which pole it is. I'm going to send him a picture of the pole. I'm going to have the part on the pole circled that is generating the noise. So it's kind of like, here it is. Here's a picture showing intense noise in this area, and we'll get into that in a second. But I make a convincing argument when I talk to the power company, and I find them to be very receptive to that kind of information.
Thank you.
Sure. So who do you contact? Well, if there's multiple issues, and sometimes there are, I pick the worst 2 to 3. You don't want to have them chase 20 things. It's just going to frustrate them, and they're not going to pay attention to you. One thing I always remind people is the RF expert, your job is to locate the pole that's causing your issue, not every noisy pole in the city. And I talked to one ham, it's maybe been 10 years now. He was using RFI mapper, and he was going out like 10 miles. And I'm going, no, don't go out 10 miles. That's not your problem. Your problem's probably within 0 to a quarter mile or 0 to a half mile. You don't need to go to the other side of the city and find the noisy power poles over there. Your power company's not going to appreciate that. You want to get your problem fixed. You know, if they want you to, find more stuff, fine, but they're not going to want you to do that. They're going to want to make you happy as a customer. So you'll have to open a trouble ticket. Sometimes that's easy, sometimes hard, depending on how familiar with the service rep is with this kind of problem. Your objective is to get either the engineer or the maintenance supervisor to give you a call. And then you say, I have some information. I can send you the information in an email. It'll show, what pole I suspect is the problem. I've usually had no problem getting an email address and a phone number from somebody. And then I send the information, and I always ask, when you come out, please let me know, and I'll be there to listen. I'd say probably more than half the time they don't let you know. They just come out on the spur of the moment when they have a slot in their schedule open and you're not notified. But if they fix the problem, the noise will get better. If you're lucky, they'll contact you, you'll work out a time, you'll be out there with them, but that maybe happens half the time. And of course, if your information is accurate, when they come out and fix the part you've identified or confirm the part and then fix it, you establish a lot of credibility. And my power company guy, I work with him now for 10 or 15 years. I report something and he's got a guy out there confirming it, and the next day, and it's like a non-issue. I mean, we have a lot of mutual trust between us. So the third tool I use, and usually the third tool is the first thing I do when I work on an RFI assist, something called RFI Mapper. Here's a picture of a route I ran maybe 10 years ago or so. And it kind of shows a lot of green. That's good. But it also shows 3 hot spots. And we'll talk about those 3 hot spots. Let me, before I go on, this middle one here is near a middle school, actually the top one. You can look at the area polluted. When I drove this route in my mobile, and I have a quarter-wave whip on the back of my truck, this side road is a quarter mile. You can see how intense this problem was and how much area it polluted. I mean, it was really a hot source. And one of the things that happened when I was out working on this, I think it was Monday or Tuesday of the week, I was out working the pole, and the resource officer, the policeman that worked inside the school, came out and said he had some reports of parents telling him there was a stranger out here doing some weird stuff with equipment. And he came out and he says, "What are you doing?" And I thought, "Oh, I'm gonna get taken to jail here, or at least detained for a while." I explained to him I'm a ham radio operator, and I'm trying to find the source of a noise problem, and I'm using an antenna. I had the dish, which a lot of people look at that and go, "What's going on with this strange device?" I explained that I located the problem. It appears to be a pole in front of the middle school, right next to the entrance drive, and I was getting the strangest look from this guy, and I thought, he's not understanding a word I'm telling him. He's gonna detain me. He's gonna call in a unit and keep me around for a while. And he said, "Is this why my handy-talkie doesn't work when I'm directing traffic?" And I said, "Yes, sir, that's exactly why it doesn't work." I says, "This thing is so intense. It was like 55 dB attenuation to quiet it down." He goes, "Oh, great. Hopefully you'll get it fixed." I said, "Yeah, the power company will be out in a day or two to take care of it." He goes, "He's great. I'm going to love to have my handy-talkie working again." So he had experienced the same problem. And it was a totally opposite result than what I expected. The way he was looking at me, I'm figuring, hey, this guy is going to challenge me. He's not getting the story, but just the opposite was true. And I've probably run across 3 police officers doing this kind of stuff. And one of the guys said, "Oh, this is the same stuff we use to track ankle bracelets." And I said, "Yeah, it is. It's the same kind of thing." So you meet some really interesting people when you do this kind of work. So why did I need a new tool? Well, I had about 10 years of experience in PLN, and some were big, some were small, intermittent, and it was during really cold weather. I remember one day I was out there, it was about 20 degrees and 20-mile-an-hour wind. It was just no fun at all. My HF beam provided a general direction, and then my HT combination, I could go out and find a pole, and they'd come out and fix it, and then it'd be okay for a while, and it'd come back. And it was just kind of getting frustrating trying to keep up with the PLN. So after years, maybe 5 years of never really getting the noise under control, I just had too many things that were happening, and this was a relatively rural area when I moved into it. And the final straw was I had a S9+10 to the southeast and an S6 to the west that I could not locate. And this is back in 2015. I just got frustrated. Said I need to try something else because this isn't working for me. So my solution was a map, color-coded map, that showed both location and magnitude of the problem. And you pick the band of choice. And for PLN work, I use 10 meters usually. It's a nice quiet band. I can usually identify down to the pole or plus or minus the pole. And as I drive her out, my laptop will tell me every 10 seconds what the level is. And if it gets above S9, it'll start announcing every second. So I hear the announcement, S8, S9, S12. I get a real good feel for, hey, is this the right area? I can then go back and confirm the pole with the HT Yagi in a dish. The map is really useful for sending to the power company because it's a visual thing. It's not up to interpretation. Here is what the RFI mapper is telling us, and it's telling us this is really a hot spot for noise. And you can confirm once the problem is fixed, you can redrive the route and you should see green. So here's the scale I use, and what I've done is extend the S meter scale above S9 because I wanted something linear and simple for people to understand. So there's an S10. S10 is S9+6 dB. S11 is S9+12 dB. So it increments up in the standard 6 dB increments for each one of the S units. When I do the mapping, the green colors are good. Yellow, orange is starting to get serious. You get into the red, they're really getting high levels. And I kind of ran out of colors, so I said, okay, let me go back to simple colors, white and black. They're really high levels if I need them. And I find anything above an S9 deserves attention. Anything above an S11 is a red flag. If it's an S11, you need to take a pretty close look at it if it's anywhere near your QTH. Here was actually one of the first maps I made. My QTH was up here to the upper left at 1.7 miles away from this noise source. When I pointed north or southeast, it was S9 plus 10, S9 plus 20. My power line guy and I had spent all kinds of time up in this upper left-hand corner. You see some orange up there, and we investigated that. They worked on some poles, they fixed some problems, but the noise never got any better. And it's really hard to work South America and the Caribbean when you have this kind of noise level. So finally I said, this isn't working for me. And that's when I put together some beta code. This is back in 2015, and said, okay, I'm going to drive every road until I basically fall off the map and drive into Lake Lanier, which is my southern boundary. It's the dam of the Chattahoochee River forms a lake. And I figured, well, it can't be beyond the lake because the other side of the lake is like 10 miles away. That's too far. So I just started driving all of the roads in the area, and here's a section of what I found. And you can see that I drove over an area, it was green, a little bit of yellow, drove south, got a little bit of yellow, and then I drove down this last leg of the map, and things started to get really nasty. And my wife was helping me at the time because it was like a very beta test, and she was watching the laptop. And we got over in this area, and she said, this is the problem, isn't it? And I said, yep, sure is. And it turned out on this main road here, there was some metal arcing on a pole. Very unusual case. Also was interesting, I found some other noise sources on a ridge line just to the right of this, to the east. Those don't bother me. They're behind the primary ridge line, so dirt is a really good attenuator, and it kind of taught me, hey, if stuff is behind a hill or a mountain or whatever, you don't really need to worry about it. That dirt's going to be a 50 dB attenuator. But on this main ridge line, it got really nasty. And so what was the cause? This bolt was arcing to a metal plate on the pole. It was a cross arm support. The lineman said he could smell something burning when he got near the top of the pole. So it was like the creosote or the preservative in the pole was overheating. They re-drilled this, remounted the cross arm support, fixed the problem. Bam, all of a sudden I go from an S9 plus 10 to an S3. So it definitely was a big problem. It's kind of unusual to see this. I've never seen one since like this. So these are really odd problems, but if you happen to be unlucky enough to have the problem, it's not going to go away until you find the problem and say, this is the pole, here's the area. Second example was an area I investigated for my power line guy, actually. He says, could you take a look at this? So I did. I produced the map and found a couple of hot areas. We're going to talk about this hot area to the top here. Here's the drill down from the map. And you can see as I drove in on the left-hand side, this map, the left-hand, or actually the right-hand lane when I'm going south, I got one really hot spot. When I drove the other direction, I got another really hot spot, these blue stars. And they were S12, so they were S9 plus 18 dB, which is pretty significant. And turns out after some investigation by the power line guy, it was a pole top insulator. So this is a good scenario where the power lines are along one side of the road, they're not switching back and forth. Sometimes you can identify right down to the pole that's causing the problem. And that's really nice. You don't have to go, well, it could be this pole or this pole. You go out there and it's like, bam, bam, it's this pole. And if you scan it with a dish, it's this problem. This one was the one I talked about earlier by the middle school. I had noise to the southwest direction, and it was weird. It was kind of during wet weather. Went away after things dried out, which is kind of the opposite normally. Traced it to a defective lightning arrestor, replaced the arrestors, all green. Now when I reran the route, thing I learned there is lightning arrestors can be very strong. The arrestors, and we'll talk about it. We talk about it right now, I think. Let me just pause this for a second. I'm going to stop sharing and should be able to see me.
Yeah.
This is one of the newer lightning arrestors. Let me see if I can get it over here where you can see it real good. It has fins on it. These fins are rubber. or something like rubber, really tough rubber. You try and cut it, you will not be successful. A friend of mine tried to dissect one of the ones he had, and it was about impossible. It's that tough. The interesting thing about this is here's what they're using today. Prior to this kind of lightning arrestor, they had a one that was a porcelain. So the insulator was not rubber, it was porcelain. You could take an ultrasonic dish and scan that thing from 200 or 300 feet away, and it would be vibrating so intensely, there was no doubt whatsoever it was the lightning arrestor. They were very easy to find. These new rubber coated ones suppress the noise from the defective lightning arrestor that's arcing internally. And they're very difficult to hear. The only way I've been successful is if I get right underneath the arrestor, point up at this bolt on the bottom, the ground bolt, then I can detect something. But if you run across one of these and you're using a dish or they're using a dish, they're very difficult to diagnose. What's inside here is a stack of MOVs that make up the arrestor, and the MOVs are chosen so that the total voltage on the 14 kV line, which peaks about 19 or 20 kV, it does not fire until that voltage gets up into the 20 to 24 range, 20 to 24 kilovolt range. So there's a stack of MOVs in here, and that's how the lightning arrestor is made, and it's coated with this rubber. Ground on the bottom, high voltage on the top. The other thing that's kind of interesting is pole top insulators. Here's a picture of one, and these things look small. This is 6 pounds of insulator, which is pretty heavy for an insulator. The high voltage line goes through this slot on the top, and it's wrapped with a piece of wire to this area below it. So the wire, the high voltage line, is held down in the pole top insulator. Sometimes those wraps don't make good contact, so you end up with arcing between the high voltage line and the wrap that holds it to the pole top insulator. I've also seen pole top insulators that have a hole in them from a lightning strike that went through the pole top. Pretty rare to see that, but I saw it was not a pencil eraser hole, bigger than a pinhole, but maybe a pencil lead kind of a hole through the top of this, and it went right through the insulator to the pin, a metal pin that holds up the insulator. All right, let me go back to sharing screen. So we've talked about this one a little earlier. Interesting experience, and this is the one where the police officer challenged me, but all turned out well. Last example I'll talk about is this area was nice and quiet, all green, until a lightning storm in June, and all of a sudden it went bad. I had noise to the southeast east area. Turns out there were multiple problems here, apparently caused by the lightning strike. 2 pole top insulators and a recloser. Recloser is like a circuit breaker that tries to reclose the circuit. Once the surge is gone, it'll try usually 3 or 4 times before it goes open permanently and has to be reset manually. So it's kind of an unusual one that I don't see too often, but there ended up being 3 problems. So for RFI Mapper, how does it operate? Really pretty straightforward. I first saw this kind of stuff back in the 1990s when I worked for a cellular company. What it does is the process, every 1 second, the GPS sends the lat long to the laptop, triggers the software to read the S meter from the radio. And I'm usually sitting on a quiet frequency on 10 meters because there's a lot of quiet up there. And once the data is collected, the program writes the lat long S meter and elevation data to the hard drive. So in doing a sample a second, 60 samples a minute times 30 minutes in a half an hour, you can collect 1,800 data points in a half an hour. And that 30 minutes at 20 miles an hour gives you about 10 road miles of data. That's a lot of road miles. You can find a lot of noise sources, more than the power company needs to fix. But at least you get a picture of what's going on. The mapping's done with Google My Maps, and it's not the same as Google Maps, a little different. It takes about 10 minutes to map it. You can map up to 2,000 data points, so about half an hour at a time, and you can do 10 of those in a particular map sequence and turn the layers on and off. So if you go over 33 minutes, no problem, you just do it in 2 layers. Hardest part, setting up a mobile installation. So what's involved with Mapper? Really three things: laptop computer, HF transceiver, and I use a really old Kenwood transceiver from maybe 30 years ago. And it's so old, the output of this thing is TTL. Some of you old timers may remember that. That's my era when I went to school. I had to convert that to RS-232 and then RS-232 to USB to bring it to my laptop. So I needed a couple extra pieces there. But basically, all the newer transceivers have USB. It's a much simpler way to go. And the third thing is a simple GPS. I bought this, the one I use. I actually have two of them now, but the first one I bought was $30. Now they're gone up to $45 or so. So when I started doing this stuff, what did the area look like? Well, here's a picture when I started to the west of my QTH, and you can see 1, 2, 3, 4, 5, 6 hot areas. And these are in red or hotter, so they're well above S9. And it was really pretty hard to hear anything in the JAs, the VKs, the ZL, that kind of DX stuff. Within a month or so later, here's a route I ran, and things looked much better in the upper part of this map. And you can see that the lightning arrestor problem we talked about earlier, we cleaned that up. And then a little later on, oops, where'd that go? Let me see if I have it here. Oh, maybe not. A little later on, I did it again, and this whole drive was green. I think I have that later on in the slides, but it's a progressive thing. If you have more than one problem, you got to kind of work the problems a couple at a time, get them fixed, and then you'll see big improvements. And I'm a little different from the standpoint, I have a 5-element 10-meter Yagi on a 90-foot tower, so I tend to hear things out farther than you're going to if you just have a wire antennas, for instance. And I'm trying to be competitive, too, from Georgia, which isn't always easy in DX contests. So does Mapper work? Yep, I've used it for more than 10 years now, identified thousands of PLN sources, probably fixed maybe 500. Once the trouble is clear, the noise should go down if you identified the right noise source. New map run should show green. Made great progress. When I started, things were pretty nasty. Now down to about an S2 on 10 meters. And if things are looking really good, I'm down to an S1 and SSB mode. Things I deal now with mostly are intermittents after the summer storms. I got to clean those up. So clearing distance guidelines. A question I get a lot is how far out you need to look for these kind of problems. And I'm talking power line problems now. I kind of have a general rule. Wire antennas, 30 feet, 40 feet, you need to kind of look out a quarter mile in all directions because you don't know what direction is the problem. If you have a 3-element beam, say 50 feet, probably need to clear out to half a mile, but at least you have a quadrant. You'll know if it's the northeast, northwest quadrant, you have a place to look, so you don't need to drive all of the roads. If you're running a multi-element Yagi at 100 feet or more, or have a phased array, you may have to go out to a mile and beyond. Like as I mentioned before, I have 5 elements at 90 feet on 10 meters. If it's not blocked by terrain, I routinely hear the larger emitter sources out to more than a mile. My longest confirmed distance was that first one we talked about at 1.7 miles. And my absolute longest was one that was out 3 miles away. It was on a 200-foot hill. And when I turned that into my power line guy and said, hey, take a look at this, I need to have this arrestor examined and replaced. The first thing he said to me was, well, I thought you only could hear out about 1 or 2 miles. I says, yeah, Vic, but this is different. This is an unusual case. He says, okay, I'll replace it. He did. And as soon as they replaced it that night, things were totally quiet to the northwest. So that was the problem. That was highly unusual. You don't normally need to go out 3 miles unless you have some special, high gain antenna sitting on a tall tower. And it's all about line of sight, right? That's what we're kind of working with here. So what noise level is normal? Well, generally speaking, I look for, when I do RFI assists on 80 meters, about an S6 is where you expect things to be. 20 meters, about an S4. and on 10 meters, about an S2, just in rough ballpark numbers. Couldn't be a little better than that, could be a little worse, but that's kind of what I think when I look at issues. One thing that's worth considering or keeping in the back of your mind is something called free space path loss. And there's a formula that predicts, or you can calculate with the formula, how much attenuation is provided as you move away from or closer to a problem. And that's the basis on which RFI Mapper works, right? As you move close to a noise source, every time you cut the distance in half, the signal goes up by 6 dB. And when you move away from it, it goes down. Same thing applies at home. If you have a noise source nearby you, you want to stay away from it as much as possible. And noise source can be your house. Lots of things in your house. My dishwasher makes noise. I had to do some remedies on that. My internet router makes, actually the power supply makes noise. My coffee pot used to make noise before I replaced it. It had an LCD clock inside of it and it made noise. But the thing to remember is use distance to your advantage. Try and stay away from noise sources. Don't put your antenna, directly over your roof, 3 feet off the top of your roof. Put it out in the backyard in the woods if you can. Sometimes that's not possible, but it's best to let distance be your friend. Move that antenna away from noise sources. That will help you when you're not hearing every small noise source. So what do you do about switching mode power supplies? Well, there's solutions for those too. If it's not power line noise, maybe switching mode. And in the lower right-hand corner, you see a picture of a couple things, one of which is my router cable modem are plugged into a strip, and they were making all kinds of noise. So I put some ferrites on those, and on the DC side, I have a box, isobar box on the AC side. It quieted them right up. I don't hear them anymore. And they were problems on 80 meters. All kinds of ferrites you can get to different sizes, small, medium, large, and then really large. If you really want to get into it, Jim Brown, K9YC, has a really fantastic website. You can spend days or maybe even weeks reading over all the information he's accumulated on ferrites. He's done a huge amount of work. One of the takeaways from this is if you do install a ferrite, the effectiveness is determined by the number of turns or passes you make through the ferrite. It's a squared, so it's an n squared times the base impedance. So if you only go through one time, 1 to the second power is 1. If you go through twice, the base impedance gets multiplied by 4. If you go through 3 times, the base impedance gets multiplied by 9. So you want to make, I always use at least 2 turns, preferably 3 turns. Some people want to go through more if you can. There's a limit. You can't go through like 100 times. But depending on the size of the cord, I try and get 3 turns through the ferrite. That works pretty well. It really attenuates the noise, and it stops the transmitter, which is the switching mode power supply, from using the power cord, which is the antenna. It basically isolates those 2 components. So you have a transmitter that doesn't have an antenna anymore, you don't hear it.
Those clamp on ferrite beads you have, do they come with the type of core they are, like type 43 or whatever?
Those are type 31s. If you look at the part number, yeah, all of them are type 31. So the part number here, I kind of broke it up, is 31 is the material type.
Okay, I see that.
Yep. Now, if you're dealing with VHF, it's different, but an HF type 31 is, mixed 31 is what you want. And I always have a supply on hand because I never know when I'm going to need multiple ones. If I go out and RFI assist, I'll bring them along. And depending on the size of the wire that needs to go through them, I use a small, medium, large. If you're using them on the AC cord, you're going to need a large, and you may only be able to make 2 passes through that ferrite. So a little bit about the results. When I first started, this red line is what I started with in 2016 as far as noise. And a month later, I squelched a few noise sources. Got much better. My objective then was S2.5, S2.5 on 10 meters. I wasn't doing too bad. I got a little bit of noise in the 150 to 180 azimuth, but things were moving in the right direction. And then a little later, looks like 2018, so about a year and a half later, something like that, some more work. My objective was S2, and I actually beat that quite easily. My worst direction was kind of towards South America, Australia. Japan was quiet, so more improvement just by keeping doing the same things. And keep in mind, I'm trying to be competitive in a contest, so it's no noise level is too low. You want to push it down as low as you can. And Europe was fantastic. You can see it was below an S1. So that was my main concern, is a lot of contacts come from Europe. You want that direction to be quiet. So a little summary of RFI locating. Clear the local area noise, LAN, first. You do the circuit breaker test, simple, doesn't require any equipment. Make sure any UPSs, uninterruptible power supplies, are off. They can be very intense noise generators. And you want to use the 137 megahertz Yagi HT attenuator to locate noise inside your QTH or near your QTH. If you find a pole, you want to work with the power company and use their dish or yours to ID the part on the pole so you know exactly what needs to be replaced. And then if you're not successful on those two and the noise appears to be out farther, use a WAN tool, wide area noise tool, AM car radio, or progress to RFI mapper if you think you're going to do this a lot. So kind of my three-step process. It has worked for me very well. There was one other slide I wanted to talk about here just briefly. I thought this would be of interest to your club, since this was a cow fence. I had done an RFI mapper run, this is back a few years now, and this area was noisy. So I got out my Yagi and I'm swinging it around, and you can see the power lines here. They're well spaced out, and I use some drop cables to feed houses and things. Area is noisy. I'm going, okay, what's going on here? You know, it's towards Europe. I want to get it down as low as I can. And I spent about 2 hours walking up and down this road trying to find the noise source. And I pulled the dish out, and I couldn't really locate, I couldn't identify, well, hey, where's it coming from? It's here, but I can't really say, which pole it is. Well, I got the dish out, and just by accident, I happened to swing it low across the fence, and the dish started chattering. I go, what's going on here? The fence is making noise. I started looking at the fence, and it was a galvanized steel fence with the joints, wraps. And it turns out these wraps were making the noise. This is not soldered, it's just a wrap. And the oxide, the zinc oxide, is not a very good conductor. What I found was when things dry out here in Georgia in the fall, usually in the September, early October timeframe, these poles, the posts, no longer are grounded. So this fence doesn't get a ground every 10 feet. It, maybe one every 20 poles is grounded, mostly down to the right here. You see it go downhill down to a creek. That is a good ground, but the rest of these are not. And apparently because this fence runs underneath the power line, enough energy is induced, enough voltage is induced in this fence that it was trying to find a way to ground and moving across these joints. So there were about a half a dozen joints on this fence making all kinds of racket. So you never know what you're going to run across. And sometimes you stumble across things by accident, and persistence gets you where you need to go. But I thought this was a little bit different because it ended up being a cow fence, which is not a normal RFI generator. And it only happens in the fall time during that really dry spell.
How did you resolve it?
Yeah.
I didn't. It resolves itself because if we don't have a dry spell, no problem. And it's only when the dry spell gets really bad that it starts making noise. And the good news was this fence is very low, and there's enough hills between, I'm off to the left here, there's enough hills between me and this fence, it's not usually a problem. Now there is another fence about 3/4 of a mile to the left of this that generates noise also, but unfortunately that seems to be better grounded. It's similar kind of fence. So basically it's not bad enough to worry about, and it happens for such a short period of time in the fall that as soon as the rain comes, it goes away. I didn't really want to approach the homeowner or the pasture owner and say, I'd like to solder the joints on your fence. Some things are worth chasing. And this one, once I found it and realized, hey, this is a really low to the ground, it's going to be blocked by hills for most of the fence distance. And you can see it kind of goes uphill. So it's not, it's not totally low. Some of it is in a little higher ground. But, odd. You run across all kinds of things. And I think that's it.
Well, I know we're pretty much at an hour, and I don't want to take up any more of your time, Jeff, but I just want to thank on behalf of the club.
Yeah.
I will say I do have, you did send me the design for the 137 megahertz Yagi, so if folks want to build that, just let me know and I can send that out. And thanks again, Jeff. Thank you very much for helping us out. And with that, I guess we'll go ahead and wrap up the talk. Thank you.
Yeah. Good luck on your good luck on your RFI problems. If you don't have an RFI problem today, you will at some point in the future.
Sam, are you going to try to get the presentation?
Yeah, I'll follow with Jeff. Thank you.
Yeah. One last comment is about a month or so ago, I got contacted by a guy that lives about 50 miles to the west of me. I'd driven over maybe about 4 years ago and done a presentation for a club there. And he wrote to me and says, I wasn't really paying close attention when you gave your presentation, but now I have RFI and I'm not sure what to do. So a good example is just file this away back in your memory bank somewhere, because someday you may need it.
Thanks, Jeff.
Thank you very much, sir.
All right.
Oh, wonderful. Thank you.
Yep. Good night.
73.